Assalamualaikum and a very good day to our lecturer, which is Sir Maman Hermana, and our fellow GAs. Today, us Group 6 is going to present our geomechanic lab presentation. We are consist of 4 team member, which is myself, Fatih Fidaus, Muan Muhammad Aizat, Jiva Bigai, and Al Fateh. Since our group member only consists of 4 team members, I volunteer myself to actually present about the static and dynamic elastic property of rock and the inelasticity of the rock, or also known as the plastic property of rock. In actually learning about the elastic and plastic property of the rock, one need to reconsider the deformation of the rock itself. And this can be explained by the stress and strain, the stage of deformation, and finally the classes of material of the rock. And for the stress and strain, we know that stress is a force applied over an area. Therefore, it have a unit force per area, and pressure is a stress where the force act equally from all direction. But if the stress is not equal from all direction, it can generate 3 kind of differential stress, which is tensional stress, compressional stress, and shear stress, based on the picture that I put here. And for stages of deformation, we can see based on the graph itself, it explains that there's three stages, which is elastic deformation, where the strain is reversible, meaning the rock or certain material can come back to its original form after given a specific force, while ductile deformation shows strain is irreversible, meaning it can't come back to its original shape. And finally, the fracture, which is at the edge of the graph. And for the classes of material, we can divide into two, which is brittle material and ductile material. And based on the observation, we see that the brittle material has a small to large region of elastic behavior, but a very small region of ductile behavior before it even reach the fracture part. While ductile material, we can see there's a very small region of elastic behavior, but a very large region of ductile behavior before it reaches the fracture part. Elastic modulus is a quantity that is used to measure the resistance of a material or rock from deformation, which involve elasticity. And the elastic modulus itself are divided into 2 kind of measurement, which is static and dynamic modulus. In definition, the dynamic modulus of rock are those that is calculated from elastic wave velocity and density, while the static moduli are those directed measure in deformational experiment. The static and dynamic moduli of the same rock may significantly differ from each other, and the main reason is that it is likely to be difference in the deformation strain amplitude between the dynamic and static experiment. In some of the experiment done by Zimmer M, he shows that in dynamic wave propagation experiment, the strain is about 10 power of negative 7, while the static strain may reach to 10 power of negative 2. And static modular are often used in well-bore stability and in situ stress application to actually evaluate the possibility of breakout, elevated pore pressure, and tectonic stress distribution. For example, a common method of calculating horizontal stress in Earth is by assuming that the Earth is elastic and does not deform in horizontal direction. This is some of the example for elastic modulus, which is Young modulus, Buck modulus, shear modulus, and Poisson ratio. Young modulus is defined as the ratio of extensional stress to extensional strain in a unit axis stress state. And we can think of Young modulus as the spring constant for a solid, while Buck modulus is the ratio of pressure applied to the amount of volume change in a particular cube. A large volume of K, which is the Buck modulus, means that a material is very stiff and the material will not compress very much, while small k contradicts it, where material can compress a lot, such as gas. Shear modulus Describe how difficult is it to deform a cube of material under an applied shearing force, meaning a large shear modulus means that the material will not change shape easily. Gas and liquid do not support shear force, meaning the shear modulus is zero. Finally, Poisson ratio. Poisson ratio is defined as the minus the ratio of the lateral strain to the axial strain in a uniaxial stress state. Inelastic or plastic property of rock can be explained by the plastic deformation of the rock itself, where the rock experiences permanent distortion that occur when a material is subjected to a tensile, compressive, bending, or torsion stresses that exceed its yield strength. Just like elastic property, it shows effect to seismic wave propagation, and different rock conditions have different elastic and inelastic property. And finally, the inelastic and plastic property of rock can help in lithology and fluid determination. Finally, the elastic and inelastic parameter of a rock. These three are the most important one, which is the P wave velocity, S wave velocity, and the density of the rock. Research done by Houzu and other researchers showed he explained that the ratio of P wave velocity with shear wave velocity can provide important information about the type of lithology, and the Poisson ratio can characterize the relationship between Vp and Vs of a material, which can affect the P wave reflection coefficient. Keep in mind that brine saturated sand has higher Poisson ratio compared to gas saturated sand. And finally, he explained that lambda rho and mu rho are combined to distinguish the fluid and lithology. Other than that, the parameter can also be used in actually detecting the direct hydrocarbon indicator of a specific well log data.
Hi, my name is Wan Muhammad Aizat bin Wan Muhammad ID, and I will be presenting the title Pressure Profile. Pressure are divided into four parts for this subject, which is abnormal, hydrostatic pressure, overburden pressure, and also formation pressure. The first one is abnormal pressure. Formation pressure can be abnormally high or low with respect to normal hydrostatic pressure. The distribution of abnormal pressure is geographically and vertically not only on elder formation, but can also occur during the recent sediment. Abnormal pressure caused by an inability of fluid to escape from the pores, which condition the existence and durations of overpressure. The consequences of abnormal pressure may be both desirable, which is for the hydrocarbon migration and efficiency, and can also be undesirable, which is unpredictable and unquantifiable, which will lead to high risking during the drilling. So when we talk about drilling, there are two strategies to overcome this. The first one is strategy, which is the drilling for the kick, which is using the minimal mud density to achieve a higher drilling rate while accepting the risk of encountering a kick. Therefore, they will have a faster drilling rate. The second one is overbalance. Overbalance drilling is keeping mud density very high in order to minimize the risk of blowing out, which is the mud losses. This will result in a slower drilling rate. Overburden pressure. Overburden pressure is a pressure at a given depth that is the pressure exerted by the weight of the overlying sediment, which is not involving the fluid. It is also called as overburden stress. This is the formula for the overburden pressure. The third one is hydrostatic pressure. Hydrostatic pressure is the pressure exerted by the weight of static column of fluid, as function of the height of the column and fluid density only. The dimension and geometry of the fluid column have no effect on the hydrostatic pressure. Fluid column height is considered to be the distance between the measured point and the projection of the well location onto the perpendicular from this point, which is the true vertical depth. Last but not least is the formation pressure. Formation pressure is the pressure of the fluid contained in the pore space of the sediment or other rocks. It is called the pore pressure. There are three categories of formation pressure. The first one is negative pressure anomaly. This pressure which is below hydrostatic pressure. The second one is the hydrostatic pressure, which is a function of pore fluid density. And the last one is the positive pressure anomaly, pressure in the excess of hydrostatic pressure and usually limited by the overburden pressure. In normal hydrostatic condition, formation pressure and hydrostatic pressure are equal. Depends on the weight of the weight of column of water saturating the pores of the sediment between the measurement points and the atmosphere. Note that a small variation in water density leads to a significant pressure difference. Pressure profile is very convenient to be used for determining the mud weight, which is also known as the mud density. It is important to prevent the losses or the gain. Okay, how do losses and gain occur? Losses occur when the mud weight is higher than the pressure of formation. Means that the mud weight will penetrate into the formation. So the other one is the vice versa of the losses, which is the formation pressure is higher compared to the mud weight. So it will lead to gain. Gain will lead to kick, and kick will lead to blowout. So one of the example we can see is the Macondo incident, which is known to be the biggest oil spill throughout the history of oil and gas. So next one is pressure gradient. Pressure gradient is very useful to determining the type of fluid inside the formation. It is also known as the FPWD operation, which is stand for formation pressure while drilling. Water will have a 0.433 psi per foot gradient, while oil usually is 0.15 and until 0.43, while gas is below 0.1 psi per foot. That is the normally in the geological operation used. It is also can be used to determine the deficiency of hydrocarbon inside the formation if the wells are connected to the other wells. Okay, I think that's all from me. Thank you.
Hello everyone, I'm Jivan Begai. Today I'll be explaining about the principal and effective stress. Before I start my presentation, I would like to apologize myself for unable to record this presentation using my face due to the technical problem in my laptop. Let's start my presentation. As we all aware of the concept of stress, which is force per unit area, but what are principal stress? Principal stress are the maximum and minimum extensional stress in a stress state at a point. The principal direction are the corresponding direction which has no shear stress associated with them. They can be defined as the normal stress calculated at an angle when the shear stress is considered 0. They can be obtained for maximum and minimum values, where the maximum value known as a major principal stress, whereas the minimum value known as a minor principal stress. There are two types of principal stresses, which is 2D and 3D. In short, principal stress explain what the maximum normal stress. By that we know how much stress the object can be experienced and at what angle. This can be used to compare against the available criteria to see how the object is going to perform at a given condition. The diagram shows the concept of principal stress on an x and y plane. As I explained earlier, there were two types of principal stress, which is 2D and 3D. 2D can be calculated by the angle when the shear stress is equal to 0. The shear stress of a point 2 relative to point 1 and the normal stress are found on x and y direction of a plane. There were two value of angle which is between 0 degree and the other is between 90 to 180. The figure below explain the 2D diagram. So, for 3D, it demonstrated three planes of zero shear and the planes are mutually perpendicular that has the maximum and minimum value. The normal stresses are referred as sigma 1, sigma 2 and sigma 3. On the algebraically order, the largest stress will be sigma 1 whereas sigma 3 will be the smallest. The principal component will be sigma 1 is greater than sigma 2 whereas sigma 2 is greater than sigma 3. The figure below shows the 3D diagram on the principal stress. Let's focus on the effective stress. There were a couple of ways to define the effective stress, which is the normal stress to which the soil particles are subjected. We will use sigma prime to notify the effective stress. In the other way, effective stress is the portion of the total stress which is actually carried by the soil grain themselves. For example, effective stress can be found between the particle to particle content in the soil system. It is not a physical parameter such as total stress. Effective stress cannot be measured but can be computed. Effective stress is critical for the importance of engineering functions such as determining the shear stress of a soil, determining how much a soil can bear before it fails, evaluate the slope stability, how much the soil settlement or the duration for the settlement to occur. The figure concluded that the contribution of the pore water pressure and the arrow found within the soil system shows the stress passes between the soil particles. Okay, so the figure shows that Carl Terzaki, the father of the model mechanism, is the first to introduce the concept of effective stress in the year 1966. Effective stress is applicable on fully saturated oil. It can include two parts. The first part explains the relationship of effective stress is related to torque stress and pore alter pressure. It has this equation where effective stress, which is the amount of stress that the particle feel, equal to total stress, where the stress due to all forces on the soil sample subtract the pore pressure. The second part concluded that the compression of engineering component and the shearing resistance are exclusively depends only on the changes of effective stress. From the figure, it concluded that in a saturated soil system, as the void are completely filled with water, the pore water pressure acts equally in all directions. It is not exact contact stress between the particle, but the distribution carried by the soil particle over the area is considered. So that's all for my presentation on principal and effective stress. Hope you guys have a brief understanding on these two type of stress, and thank you very much for your time.
Hi, my name is Muhammad Fateh and I will be explaining on the seismic attributes for fracture and faults identification. Basically, seismic attributes are very useful in the characterization of faults and fractures in 3D seismic data volumes. Seismic attribute can provide alternative images of faults and channels, and also structural deformation history. It is particularly useful for identifying faults, large fractures, and zones amenable to fractures that fall below seismic resolution. There are many types of attributes for identifying fault and fracture, but for today, I will be explaining on three attributes which are coherence, curvature, and also structural smoothing. First is coherence. Coherence is a measure of similarity between waveforms or traces. The seismic waveform is a response of the seismic wavelet convolved with geology of the subsurface. That seismic response changes in terms of amplitude, frequency, and phase, depending on the acoustic impedance contrast and thickness of the layers above and below reflecting boundary. The calculated coherence volumes dramatically enhance the ability of the interpreter to observe the structural and stratigraphic discontinuities. For example here, in figure A and B, we show a comparison of time slice through the seismic amplitude and coherence volumes. The coherence volume was generated using a modified eigen decomposition algorithm, which employs a robust deep steering option for removal of the structural component, which is deep, from the coherence computation. Notice that the clarity with which the fault patterns stand out, which would be difficult to identify from the seismic alone. A chart display in figure C shows the correlation of the fault patterns with the seismic signatures. The next attribute is curvature. Basically, curvature is one of several geometric seismic attributes which measures how bent a curve is at a particular point on two-dimensional or three-dimensional surface. Understanding and improving the imaging of the shape of curve in seismic data allows improved understanding and interpretation of features in subsurface data. For example here, the figure shows a comparison of time slice through the seismic amplitude, coherence and most positive curvature volumes for a 3D seismic volume from the North Sea area. Notice that while the coherence display is featureless in the areas of high coherence, which is white areas, the most positive curvature shows significant structural deformation in the clay marker. Any interpretation carried out on the curvature attribute needs to be correlated with the seismic to make sure that the attribute makes geological sense. And in figure C, it shows that a chair display for seismic, which vertical and a time slice from the most positive curvature volume. And the feature seen in red color, which shows high value of curvature, correlates with reflection that show localized anticlinal structure. The last attribute is structural smoothing. The structural smoothing attribute enhances the seismic event continuity parallel to the estimated bedding orientation, and option is available to enhance edges and faults during the smoothing operation. For example, the figure A showing the original seismic data and figure B showing the seismic after generating a new structural smoothing seismic volume with good resolution and continuity of the seismic events. It helps to remove the background noise and enhance the appearance of seismic events. Thus, helps the interpreter to clearly interpret the faults and also fractures that contained in the seismic volume.